Got the Hangout running. We might as well put the Hangout up there as well. Shoot, I'm not going to put the IRC channel up. Okay, when they're ready. Yep, just let me know when it's on. It's on? All right. So, good morning, everyone. So, my name is Karim Yaghmour. And over 4 sessions, what we will do is take Android apart and kind of put it back together. All right? So what I would like to do, though, is first start by kind of making sure I have a good handle on who's in the room here. So who's got any sort of embedded Linux experience? All right. Android platform experience? Android application development experience? All right, awesome. Okay, so as the gentleman kind of gave as a prelude this morning, I wrote the O'Reilly book on embedded Linux about a decade ago. I'm putting the final touches on the embedded Android book for O'Reilly. I'm kind of like the embedded GIMP they take out of the closet every 10 years to write a book on the topic. So I've been around open source for a very long time, at least for my relative life. Since the mid-90s, I'm most widely known for having written the Linux Trace toolkit. Fortunately, somebody's doing a much better job in maintaining that today than I was. I know quite a bunch of stuff, but I don't know everything. Okay, that's the important thing. So you might have a question for which I have absolutely no answer, and we'll try to help you out in as much as we can. Sounds good? Okay, these presentations are meant to be interactive. So if you have any questions as I'm talking, please, by all means, I get better as I get questions. All right? So bonus for whoever lands the first question. Alrighty, so when I'm not doing these talks, I'm doing training, helping people out, put Android and a whole bunch of stuff and so on. So this slide set, which has about 50-some slides, which I'll put up there once I'm done, usually takes a bunch of hours to go through. All right, so we're going to try to maximize the 45 minutes or whatever's left of those that we have. The first thing I want to start with is kind of a prelude about Android in general. Android is very big. All right, just to give you an idea here, Gingerbread, which is about 2 years old now, was 3 gigabytes when you downloaded it, and when you built it, it generated something like about 10 gigabytes worth of a directory. These days, if you get yourself Jelly Bean, it's about 10 gigabytes, and it will generate about 25 gigabytes of a directory, fairly large. All right. The laptop I had before this one, which is kind of similar to what Zach has, it's a W520 quad-core i7 with 8 gigs of RAM. Would take about 20 minutes, and yeah, RAID 1 hard disks. Would take 20 minutes to build Gingerbread. It takes about 80 minutes to build 4.2. All right, so by all standard, it's pretty huge. The other thing is that it moves very fast. Every 6 months, they do a code drop, throw the code over the wall, and we get to contemplate what they've been doing. And essentially, during those 6 months, they're doing the development behind closed doors. So unlike other open source projects, you can't go to a mailing list and kind of find out, what are they up to. Okay, so that kind of makes it a little bit difficult for any sort of work with Android because there's no reference as to why did they did this change or that change. It's very difficult. You have to just diff it and try to understand what's going on. Okay, so some basic concepts. I'm going to run through these very rapidly just so we have kind of like a common lingo going on here. These are the concepts that app developers would face if they're developing an application. Okay, first of all, apps are made of several components. All of the components are activated independently of one another. How they get activated will depend on what's called intent filters. And essentially, you've got 4 core components: activities, which are UI elements; services, which are akin to background daemons. You have content providers, which are databases; and broadcast receivers, which you can think of as very high-level interrupt handlers. Or generally speaking, events like the battery's low, a new picture's been taken, the USB's been plugged in, that kind of stuff. Okay. So there is no kind of start point where you have a void main void where you're initializing stuff. It just all happens kind of object-oriented fashion all the time. The thing that keeps the components kind of tied together is this mechanism called intents. All right, intents are passive objects. They're just a data structure. It's how you shoot it out and the rules that are in the system that will dictate what happens. So for example, if I have an email client application, and essentially it starts up by the user clicking on the icon on his home screen. He gets a list of emails, clicks on the email, gets the content, and then wants to see the PDF and attachment. What will happen is an intent will be shot out saying view PDF. And then some other application will come up and actually show the actual content. All right? Applications actually get started and stopped automatically. All right? There's no start and then stop. Manually. So what happens is the system's behavior is predicated on low memory. All right. At some point, there will be no more space to run stuff, and the system will have to go out and kill something that hasn't been used for a long time. Hence, app developer has to have to implement a life cycle for the application. All right. And this life cycle essentially is a set of callbacks. And if the app developer has done its job of providing the right callbacks, then everything kind of works out as it should. This is kind of like an example of one of the life cycles, in this case the activity, which is kind of like the main user interface element. And then the other thing is that all the components that you describe and the filters for an application go in what's called a manifest file. It's essentially an XML file that says, here are the components, here's how they react to the system, here are the permissions they need, etc., etc. Everything in an Android app runs in a single Linux process, single-threaded, unless the developer does something special. All right? So unless the developer is actually starting a thread, it's all running in a single Linux process. If he has 22 activities, essentially user interface components, all of them will run in a single Linux process. Okay? And the last thing that app developers have to think about is how remote procedure calls are made. They're done through a mechanism called binder. Android doesn't rely on the System 5 IPC or, at least for app communication sockets. It uses the binder mechanism, and I will delve into that in much greater detail. Okay? So I'm speaking a little bit fast here because I just want to get those things out of the way so we can get into the internals as fast as possible. The framework an app developer has to deal with, regular stuff that app developers would have on any platform, text boxes, buttons, you name it. It's all based on the root elements called the view, and everything kind of goes down from the view. And hopefully by the end of the session, I have some time to actually show you how the display mechanism works in Android. Otherwise, this will just overflow in one of the other sessions that we have later this week. OK, data storage. One thing I want to highlight here, the app developer API makes a distinction between what's called internal and external storage. Just think of it this way. The external storage is what you have access to if you plug the device into your computer via USB. All right? This is where you can get the pictures off, put some music on, and that kind of stuff. The internal storage isn't accessible through that, although that's what's used by the system for permitting apps to store data and so on and so forth. OK, one crucial thing here is that the entire security model in Android is based on user IDs and group IDs. OK, this is really fundamental. This is why applications can't actually talk to hardware. Okay? If you're familiar with Linux a little bit, you know that hardware is accessed through /dev entries. These are nodes in the file system. And these nodes can have different permissions. And what happens is those nodes end up belonging to processes which are privileged. Okay? And for apps to get access to the hardware, they have to talk to those privileged processes. Okay? And I will show you what that means practically on an architectural level in a few slides. Now, just a word on native development. You might have heard about native development with the native development kit. For app developers, that's cool for running code on the metal. For platform development, it's somewhat useless. Okay? And I can dig into that later on in the next session when I talk about the Android open source project. Okay, which is where I wanted to get to, the architecture. Okay, the architecture in classic embedded Linux system looks like this. You have the Linux kernel at the bottommost. You have a C library. You have BusyBox running up there, and whatever custom application that is going to be embedding whatever functionality you're looking for. Now, you look at the hardware that Android is working on. This is what it looks like. Okay, at the heart of it, you have a SOC. ARM-based, presumably. And then a whole bunch of stuff connected to that. The most important thing here is that you have another processor called the baseband processor, which actually takes care of the RF communication, completely separate, so to speak, from the application processor, which is the SoC. All right? Everything that Android has to talk to is connected in some way, shape, or form into that SoC. What a SoC looks like is something like this. You have some kind of networking kind of interconnect, and then everything is kind of connected to that thing through that interconnect. All right? So the processor, which is ARM, can be connecting to a whole variety of different things. The GPU may be different from one ARM SoC to the next, and so on and so forth. And this is the slide where I want to spend some time and actually slow down the pace. All right. So anything you know about Linux has changed in Android. All right. So anything north of the kernel is completely different. Starting from the Linux kernel going up, what's different about the Linux kernel? Well, they've added a bunch of different things. Yes, sir?
Can we just stop real quick?
Yep.
Well, for a technical difficulty, I think what we should do, I'm sorry everybody, this is the first time we're kind of doing this, so I think if we connect to the Hangout from your laptop, then we can show the slides, and then people will be able to hear you and see your slides.
Okay.
What do you think?
Okay, my brain's not functioning. So
okay.
would you have a USB key where I can put you the PDF? Maybe that'll be easier for me.
Yeah.
Okay.
But well, actually, so if you
or I can try to email it to you, but my networking's been so slide 23 if you want to go from there. Alrighty. So before the segue, they've changed a bunch of different things in the Linux kernel to make it possible for the user space that you see up there to actually run. All right. So they added a mechanism called wake locks. The wake lock mechanism is layered on top of the power management that already exists in Linux. You have to think of it this way, right? If I grab my phone and I put the power on, it will come up. And after a few seconds, it will kind of dim and go back to sleep. And you want that, right? You don't want the same mechanism as my laptop where essentially I have to close the lid to actually go to sleep. I have to do something manual. So what they've done is they implemented something called early suspend, which aggressively tries to suspend the system as early as possible and as soon as possible. However, in some operations, you actually want to keep the device awake because the user's typing something or he's doing something or not there on his phone. So therefore, you grab a wake lock. All right? This mechanism was probably one of the most contentious, if not the most contentious mechanism they've added to the Linux kernel. I've been involved in a number of flame wars. They usually span 200, 300 emails. That one spanned 2,000 emails and wasn't over. Okay? So eventually, they relented, and that mechanism has kind of been reworked. And the resulting mechanism has been merged into mainline, and it is planned that at some point in the future, the AOSP will start using that instead of the wake lock mechanism. All right? There's another mechanism there which is called LOMEM. It's a driver that kicks in, essentially implementing the policy which I mentioned earlier, which is to allow the user to run as many apps as he wants, and then only kill off the stuff that's been least recently used. Right, so this kicks in before the out-of-memory killer of Linux kicks in, which is the default killer, which just goes around and kills the biggest thing out there. Okay, you don't want that, because the biggest thing may actually be a legitimate system service or something running or another. Then they have the binder mechanism. The binder mechanism is the key component that allows all of the existence of what's above. All right? If you read up on binder, and I invite you to do so, go looking for Open Binder. It's essentially a mechanism that was first implemented in BOS, then actually kind of moved over to Palm, and then before Palm kind of knifed the project, the engineers that were working on it were able to get it open sourced. So there's this Open Binder thing out there. The binder mechanism in Android is not a direct inheritor of that in terms of source code. They've re-implemented it for binder, but the folks that were working on Open Binder are the same that are working at Google on binder. And the explanation they put forth is that the binder mechanism is for allowing you to run an object-oriented operating system on top of a general-purpose operating system. So the object-oriented operating system in this case is the system server and all the services that it has, all right? And the general-purpose operating system, of course, is Linux, all right? You have ASHMEM, which stands for Anonymous Shared Memory. So they're not using the System 5 shared memory stuff. They're using their own custom shared memory mechanism. And one of the key features of it is that it can reclaim or shrink allocated regions if the system is under memory crunch. All right? So it can allocate buffers, but if for some reason the system is tight, it will start reclaiming them. There's a logger driver in there, there's an alarm driver, and so on and so forth. All of these things are crucial for the user space that you have out there to run. Okay? Now you start moving up the layers. In the libraries, you have a whole bunch of libraries that everybody knows about, like OpenSSL, WebKit, and so on and so forth. But the key thing is they're using a C library called Bionic. They're not using glibc, they're not using microclibc. Okay? The main feature of Bionic is that it is BSD licensed, not LGPL licensed as glibc and microclibc are. All right? So it has less features than those things, but it is BSD licensed. And we can have a discussion about licensing in the hallway if you want later on, what that means and what that implies. Moving over on the side here, one of the most important things that they have is hardware support and user space. Okay, this is a very big departure from the way things were done with Linux, generally speaking. And what they've done there is that instead of having the upper layers talk directly to entries in /dev, which is the way it usually is done in Linux, instead the upper layers are expecting HAL components, or HAL modules to use the proper terminology here. So those HAL modules will eventually talk to the drivers in /dev, okay? But how that happens and what they're doing there is beyond Android. It doesn't care. All it cares about is being able to find the proper HAL module that implements lights, that implements GPS, that implements a hardware composer, whatever it is that they need to run. They look for that module. All right? Insofar as that module exists, Android thinks the hardware is functional. There's a whole bunch of native daemons there also in user space that do a variety of different things. And I'll cover those when we get to the native Android user space, I think on Thursday or Wednesday, I can't remember anymore. Then they have their own init and this tool called Toolbox. So who knows what BusyBox is? All right, so essentially on any Unix system, there's a whole bunch of command line commands that you can type. You don't want to have to go around and actually compile each one of these to get yourself a functional embedded system. So somebody kind of felt the need at some point. I lost my screen. Zach, what are you doing?
It's fine. Just keep going.
What is this strange montage? I can't see anything. I'm not getting any signal.
Oh.
Alrighty. Okay, so BusyBox, as I was explaining, essentially instead of compiling every tool that you have on the command line one by one, what you want is have to compile only one thing. So that's what BusyBox does. You have one binary that gets generated, and everything is a symbolic link to it. When you type ls, it executes BusyBox, and what BusyBox does is check the first parameter on the command line, which is the command you typed. It does a switch case and runs whatever that is. All right? BusyBox is GPL licensed. What you see throughout the stack here is they tried to get rid of as much GPL and LGPL as possible. So they got rid of BusyBox. They implemented something called Toolbox, which is a lot less featureful than BusyBox. Not to say it sucks, so if you excuse my French, but that's what the way it is. All right. But that's what it is. Toolbox is BSD licensed. The interesting thing is they're running their own init. So init is the first process. The last process the kernel starts. And then the init is supposed to take care of starting everything else in the system. The interesting thing about the init they have is that it manages a global set of properties which can trigger behavior in the system. All right? So you can say, if this value goes from A to B, execute this command. And this is exactly what happens actually when you go in your phone and you say, enable USB debugging. It flips one of the variables, and that causes ADBD to start. ADBD is the daemon on the target that allows you to connect to your device and actually shell into it, copy files, and so on and so forth. Now, right on top of that, you have Dalvik, and on top of Dalvik, one of the most important things running is the system services. As I said, that's the object-oriented operating system running on top of Linux. There are about 70 system services in the latest version of Android. They kind of grow 4 or 5 at every release, so they had about 15 gingerbread. This includes Window Manager, Activity Manager, which implements the lifecycle I mentioned earlier. It includes the surface flanger. Everything important happening in Android is in there. If you look at the documentation made available to app developers, there's virtually no mention of this, okay? But as a platform developer, this is probably the most important thing you need to know about. Because whenever you implement anything, it will eventually have to talk to one of those system services, or the reverse, right? That system service will have to talk to whatever you're implementing, all right? So those system services are then available to the apps through the binder and through the app API, which is accessible to app developers. So that's the architectural layout of Android, kind of like in a quick intro format. All right. Now, that diagram is interesting, but how do we get to it? You know, what are the steps in the startup that actually lead to having that architecture running? So I'm going to run you through the initial stuff pretty rapidly. There is some code inside the AOSP about the bootloader. The most interesting thing about the bootloader Android expects is that it has to implement a protocol called fastboot. Fastboot is essentially both a protocol and a tool in the AOSP. AOSP is for Android Open Source Project, which is essentially the source base that you use to actually compile Android. So fastboot allows you to essentially talk to your bootloader via USB, instead of actually shelling into it through a terminal over RH232 and typing in several commands. So it's very useful for testing purposes. So you can script a thing where essentially it flashes a new image, runs a test, and then reflashes and continues on and so on. So if you look in the storage devices used for Android, whether it be NOR or NAND flash, or whether it be an actual eMMC as in a hard disk, it uses several partitions, and those partitions are mounted with different writes, all right? And I'll get to the permissions when I talk about the native Android user space over on Wednesday. Okay, so the kernel starts up as it usually would, no difference at this level. Init, the Android init starts off, it starts setting up a bunch of daemons. One of the most important things it does is start this zygote thing, okay? What is the zygote? A lot of people look at the PS of their Android or their platform like, all right, what is that? And why is it, you know, why is it that all apps are kind of inheriting or directly descending from this? So to understand the purpose of the zygote, you have to kind of set aside this internals discussion and think about two things. First of all, there's a mechanism inside the Linux kernel which is called copy on write. The way you create processes in Unix and Linux is that you use the fork system call. If you know what fork does, it just copies the process, the parent process exactly as it is into the child process, and so on and so forth. Now that uses up memory, of course. So Linux does an optimization called copy on write, when you fork, what happens is that the fork has all its pages mapped onto the first process's address space. So in other words, you're not taking any more memory, all right? Instead, what happens is when the child process tries to write to any of those pages, that actual page is copied over. All right? So you can do 10,000 forks and you only have one copy in RAM. Right? So that's the first thing I wanted to explain. The second thing I want to explain is that in Android, one of the design goals is that when the user starts an application, it has to start fast. All right? We can't expect the user to kind of wait for the app to load. Right? He has to click and the thing comes up. So what they've done in Android is essentially they're using the copy on write mechanism to make sure that the apps start fast. And how are they doing that? They start a process which has essentially an active virtual machine, and it has all the classes that an application could ever need preloaded into its address space. All right? So that's what the zygote does. And when you create an app, you're forking directly from the zygote. So what are you doing? You're getting a warmed up Dalvik virtual machine, and you're getting all the classes that you could ever need. So then the startup is fast. All right? So that's what the zygote does. One of the other things it does is actually start the system server. And then the system server starts all the system services that are required for the system to run. One of those, as I said, is the activity manager. And one of the last steps the activity manager does is send an intent called category home. And what that does is start the application called launcher, which is the home screen that the user has. And this is how we get an actual home screen on the device. Right? Any questions so far? Right. Okay. Right. Yeah, I'm speaking very fast because that's not my usual pace, but we have a very limited amount of time. Hopefully we can kind of continue the discussion in the hallway and through the other sessions if you have any questions. All right, so I kind of told you about the Androidism, so let's skip over that. Now, hardware support in Android, as I said, is done through the HAL layer. So I could walk you through every one of those, but it's not really worth it. Essentially, just think of it this way. Every time Android has to talk to hardware, it looks for a module that can talk to the hardware. And that module is essentially .so, a DLL if you're familiar with Windows. And so long as that SO is there, then everybody's happy. All right, the native Android user space. And I'll talk about that in more detail on Wednesday, but essentially, on Thursday. If I'm shelling to the device, what the heck am I seeing? Right? Does that look like Linux? Yes or no? Some parts of it do, some parts of it don't. So there are directories that you have seen in Linux or would be written normally in Linux, like /etc, /dev, /proc, and so on and so forth. But there are directories which are specific to Android, namely /data and /system. These are the core directories for Android to run. Okay? And the meaning of those two directories will become more apparent when we get to Thursday's session and talk about the native user space. But everything that's important is in those. And kind of one thing that I would like to highlight kind of from the get-go is that one thing Android doesn't use is /bin and /lib. Right? /bin and /lib in any Unix system are crucial for the operation of the system. And if you ever design an embedded Linux system, you know that that's where your libraries go and when your command line tools go or whatever default application you might have. Android doesn't use those at all. And that's cool because that means that we can take a classic embedded Linux stack based on glibc and kind of shove it in there on the same file system and there's no conflict at all. All right. How are we doing on time?
Not too bad. We got about 14 minutes.
14 minutes to go. All right. Here's about 30 slides in 14 minutes. All right. I'll try to not kind of cut things out. So what I'll do is whatever I haven't covered today, I'll cover Wednesday. All right? So the Dalvik virtual machine. So you may hear a lot about Android using Java and so on and so forth. For all practical purposes, Dalvik just works from whatever embedded work you're doing. You just have to have it there. I've never had to kind of dig in there and tweak anything inside of it or help anybody do that, though some people actually do try to optimize it. The interesting thing is to look at how is it different from, say, standard Java. Now, if you're familiar with Java, Java stands for more than just the language. Okay, there's the compiler. There's the virtual machine that runs the bytecode coming from that compiler, and there's a whole set of libraries which essentially every Java developer is accustomed to using. In the Android world, we're still using the same compiler, but the virtual machine is called Dalvik. It's a clean room implementation of a virtual machine. And the other thing is that the libraries are coming from Apache Harmony, which is also a clean room implementation of the JDK libraries. All right? Now, if you look at if you go to YouTube and you Google for Dan Bornstein Google I/O, you'll find a 2008 Google I/O presentation by Dan Bornstein, who's the guy that designed the Dalvik machine, where he explains how it works, what are the decisions that came into making it do what it does. So they have a bunch of bullet points where they say, oh, well, it's for low power systems and limited amount of RAM and so on and so forth. But think of it this way. When you look at what happened in the Oracle versus Google trial, it becomes apparent that kind of licensing has to do something with the decisions they make. And from my perspective, it seems to me that Dalvik is a prime example of this, where instead of going with the JVM, which is owned by Sun or Oracle, they wrote their own thing, so therefore they didn't have to ask the time of day, or so to speak, from Oracle / Sun. All right. So there's a whole bunch of different things about Dalvik. The most important one is that it doesn't use class files, it uses DEX files, which are essentially class files post-processed by a tool. All right, just take a class file, run it through DEX, and it gives you DEX files, and that's what Dalvik runs. The other thing is that it has just-in-time compile. So in other words, instead of interpreting bytecode, you're actually running native code that's been converted from the bytecode over to native code. Okay? Now, of course, Java is interesting, but at some point you actually have to do something useful. So you have to go into C, all right? And the way you do that is through the Java native interface, or Genie, or whatever, however you want to pronounce it. The interesting thing about this is that it's commonly known as ancient Greek, which is to say not at all. So JNI is not well documented. There is one document out there that used to be available from Oracle's own site. It was a PDF, and it's actually a book from Addison Wesley, so you can still get it out there. And I used to joke at conferences that you better get it fast before it disappears. And at some point, somebody raised his hand and said, well, it's no longer there. Apparently, if you Google these days, you actually do find a PDF, though it doesn't seem to be from Google. Anyway, JNI is kind of like the glue layer that allows you to go from Java to C and vice versa. Okay? And hopefully, when I get to Friday's session, which is about the system services and all that, I'll get the chance to show you what that means in terms of code, in terms of if you want to write your own, how does that look like? All right? The system services, there's a whole bunch of them. They're a whole wild world of their own. I have some stats which I'll show you on Thursday. There's a tremendous amount of code in those things, and it is absolutely not documented anywhere. All right, your only resource is really the sources of those system services. So just to give you an idea here, so in my previous diagram, I showed you all the system services as being like one box. That's actually somewhat of a lie or a simplification. This is really more what you actually find on, say, a 4.2 system. So you have a set of Java-built system services, and one C system service which are running in the system server. If you type PS, you will find system_server running. That's what's running this stuff. Then you have the Surface Flinger, which is running as a separate service. The color coding here is that the gray stuff is in C, the yellow stuff is system Java, and then the orange stuff is applications. All right. Then you have the media service, which is running all the audio stuff and the stage fright multimedia layer. And then you have the phone application, which is a special application running a system service. So, of course, if you followed my very rapid intro to app development earlier, you might have noticed that I was talking about apps having services. The key difference between an app service and a system service is whereas an app service is lifecycle managed, in other words, it can be stopped and restarted, system services go from boot to reboot. All right, they are not supposed to be dying. The phone app is a special app because it uses it sets the persistent flag to true, which tells the activity manager not to lifecycle it. All right, and we can talk about that a little later on Friday. So those system services, if they want to talk to hardware, they're going to go through the HAL layer. All right, so they're going to go interfacing with the monster I have in the other slide, two slides down. But just to give you an idea, here's how an app developer would talk to a system service. He would essentially call on this get system service call, get himself an object, and then do object dot call the actual method of the object. It looks fairly innocuous from the app developer's perspective. There's a lot of plumbing going on underneath, though. All right, and hopefully on Friday we'll be able to kind of walk you through that and what it means. How much time?
About 6 minutes.
6 minutes. I might actually make it.
No, you're 8 minutes.
8 minutes. Wow. Maybe if I wait a little. Okay. All right. The activity manager. So the activity manager, as I said, is what implements the lifecycle for applications. If you've ever seen an application not responding, this is coming from this component. If you look at how the intents are dispatched, it goes through this. Anything really kind of important having to do with system goes through that system service. It's kind of similar to what the scheduler does at the kernel level. It's as important as, if a comparison can be made. All right? So just to give you an idea here, here's what goes on when you actually create a new app. If I click on an icon, right, on my launcher screen, essentially what will happen is there's an on-click listener from the launcher. The launcher is an app like any other app, and it, just to receive a click, and it identifies where that click was, and then it actually talks to the activity manager and says, oh, by the way, the user wants to start this app. Right? Activity manager turns around, opens the socket to the Zygote, and says, here's a Java class. Please start this. All right? And essentially what happens then is that the Zygote forks and then starts the new app. And this is why if you type PS on any Android system, you'll see the Zygote SPID, which let's say is 32, and then all the apps will be a direct descendant of this. Okay? I'd show you a demo, but the weird montage we have here is fragile, so we'll leave it as that. Hopefully we figure something smarter than this by mistake. All right. The binder mechanism. Okay, as I said, the binder mechanism is the key that makes the whole kind of clock tick here. So it is a driver, and essentially you can think of it as a pipe of stuff going back and forth between a caller and a callee. Okay? Here's the diagram of how it works. It sounds, very complex, but let me kind of walk you through it in an easy fashion. So just assume that when the kernel starts up, you have the driver at the bottom layer and that's it. All right, nothing else on the top is running. So that driver, okay, has a special I/O control call, which is set the context manager. All right, and the first process that comes along is this service manager on the left-hand side here. This guy starts up and talks to the binder driver and says, "I'm the context manager." All right. And once he's done that, anything in the system that tries to talk to binder ID 0 ends up talking to the service manager. Okay? And I kind of only found that out the other way around. I was kind of walking down the stack trying to understand how the actual apps talk to system services, and then at some point you'd see talking to binder ID 0 or magic binder. I was like, wait, magic binder, where's that documented? And you can only see that when you go to the driver. Okay, the driver says, okay, he's trying to talk to binder ID 0, that's the context manager. So what happens after the service manager starts is that you have the system server comes up, and then he starts every system service one after the other. And what he's doing after that is he actually talks to the service manager and registers that new system service. So at the end of the boot, what you have is the service manager is a yellow pages of all system services running in the system. It is essentially, it actually has essentially kind of like a database with key value pairs. All right, you give it a string, it gives you an ID. And when an application starts and wants to talk to a system service, it asks for the service manager. It says, I want the power manager. All right, he returns the binder ID, and using that binder ID, he can actually talk to that system service. The interesting thing is it doesn't matter which process that system service is running in. It's inconsequential. The important thing is that it's registered with the service manager. Then you have a whole set of tools that can actually talk to the service manager, like dumpsys, you have service, and so on. And I'll show you some of those when we get to the talking about the system services on Friday. So far, so good? Okay.
4 minutes.
4 minutes. Awesome. Okay, the hardware abstraction layer. Okay, so we were doing a 2 weeks ago, right? We were doing a experts panel on essentially is Android the new embedded Linux? All right, and one of the people that were on stage, not Zach, was saying that one of the reasons that Android will never kill embedded Linux is because of this. Because essentially, if you go from the app layer all the way down to the hardware layer, you got about 7 layers to go through. Okay? So it looks contrived, it looks complicated, but you have to understand that the reason behind it is licensing. Okay? So device drivers, which are inserted in the kernel, ought to be GPL, or at least that's the conservative way in which to read the licensing of the kernel. And if you follow that mindset and you kind of attach a corollary to that, which is manufacturers want to keep some of the stuff proprietary, well, the only way to resolve this is to kind of shoot some of the stuff in user space. And that's exactly what Android's doing. All right? So they put some of the brains of the drivers into a HAL module, and then they have the driver doing some kind of basic stuff. The user space hardware module, given that it's in user space, can be licensed under whatever license you deem appropriate, including a proprietary license. So that's interesting from a kind of, at least when you look at it from a very rapid point of view, managerial, business-wise, all right? But from a developer's perspective, it's a nightmare, all right? Because whereas in the kernel, you can just go to the drivers directory and find a whole ton of drivers that you can inspire yourself from, you won't find such a thing with Android. Okay, there are a handful of modules that are available in open source because kind of Google does the effort of trying to put those open source when they work on a lead device with a given manufacturer, but that's the exception, not the rule. For the vast majority of cases, you just don't have enough examples to start with. So the best place to start for an embedded developer is, ironically, to talk to his SOC vendor. Of course, you guys may be working for SOC vendors, and it's your job to actually figure that out and get those modules implemented. Okay? So the system services will go through the HAL to talk to those modules, which will then talk to the hardware. The interface between the module and the dev entry, that's yours to determine. Android doesn't care. What it cares about is the contract between the system service and the module. That's documented in a header file, and you have to conform to that. All right, and then there's a whole bunch of stock Android applications in the AOSP, and I'll reserve that to Wednesday when I talk about the AOSP. We'll dig into those later. How much? 1 minute. All right, I'm not going to ruin this part, so I will take a few questions instead. I will delve into this part of the stack, which is really interesting. How does the display mechanism work in Android? I'll defer that to, say, probably Thursday or Wednesday, and maybe take a question or two here.
I have a question if nobody else has a question.
Absolutely.
Tyler has a question. Tyler.
Yes, could you talk a little bit about the decision to use binder and ashmem versus System 5 IPC?
Okay, very good question. Why they use ashmem and binder instead of System 5 IPC? If you look into in the AOSP, and I can point you to the right file later on, they have a file which says, whoever took the decision says, well, there's a problem with System 5 IPC, and here's what it is. All right. And essentially, the key here is that System 5 IPC can lead to resource leakage, even if it's properly used. So essentially, they put that on the side, and they not using at least the shared memory stuff. The binder part seems to be more ideological. And the joke here is I was doing a presentation about this at the end of Con in early December, and telling the story of how Palm wanted to kill off binder, and then the guys who were working on it were able to get it open source. And as I was explaining this, the guy raises his hand and says, I'm the manager of Palm that knifed the project. And essentially he explained that binder wasn't really liked as a mechanism, but that it was very much dearly loved by a certain group of people, and that those people eventually moved on to Google and worked on Android. And in fact, if you go to the Open Binder webpage and you look at the names and you look at the roster of the Android developers, wait a second. So that's essentially where binder is coming from. Now, moving forward, binder right now is in the staging directory of the kernel. It is not foreseen that will ever make it into, strictly speaking, mainline. There's some work that's being done by Greg Crow-Hardman, which is projected to possibly replace it and layer binder on top of it, but maybe John knows better than I do.
There is a chance that binder might be considered like IP, where it's not something that police can design what we support to have ability users, and so it may
just make it in.
From that perspective.
All right.
I think there's going to be a lot of attempts to do the right thing.
Okay. All right, so there you have it. He knows better than I do. All right, so we're just about out of time here. So as I said, the stuff that I axed out of the presentation, I'll cover in the rest of the week. And I'm here till Friday, so if you have any questions, just feel free to talk to me in the hallway or something. All right? Thank you, folks, and you have yourself a good conference. Thank you.
So